A uniform ladder AB of length 2a and weight W has its end A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4. So there is a frictional force at this point here. The end B of the ladder is resting against a smooth vertical wall as shown in figure 1. So there's no friction at point B. A builder of weight 7W stands at the top of the ladder. So there will be a weight force here at point B going downwards of 7W, which we'll draw in a bit. To stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the end of the ladder at A towards the wall. So there will be a force of P towards the right. That's what stops the ladder from sliding down the wall. The force acts in a direction which is perpendicular to the wall. The ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes an angle of alpha with the horizontal ground where tan alpha is equal to 5/2. So let's just draw a quick triangle for that. So if tan alpha is 5/2, let's say this is alpha, opposite is 5, adjacent is 2. This would be root 29 using Pythagoras, and then using SOHCAHTOA, sine alpha is opposite over hypotenuse, and then cos alpha would be adjacent over hypotenuse. The builder is modelled as a particle and the ladder is modelled as a uniform rod, as we were told in the beginning. We want to show that the reaction of the wall on the ladder at point B, so basically the force at point B over here, has a magnitude of 3W. Okay, so let's just draw our forces on the diagram. So we have a reaction force from the ground, let's call that R1. We have the reaction force at point B, call that R2. The builder stands at point B, has a weight of 7W. The ladder is uniform, so the weight acts directly downwards in the middle. That's W. There's a force pushing towards the right. Let's call that P. And then we have friction at the ground as well. Not friction at the wall, we have friction at the ground. It either acts towards the left or right, depending on how hard the builder's assistant is pushing the ladder towards the right. And actually, in part B of the question, it asks us to find the range of possible values of P for which the ladder remains in equilibrium. So basically, for part B, we want to think about how big can P be, how small can P be, such that the ladder is still in equilibrium. If the builder's assistant applies the minimum amount of force, that means the frictional force will act towards the right to help keep the ladder in place, to oppose it from sliding down the wall and therefore to the left at A. And if the builder's assistant pushes too hard towards the right, the frictional force will actually act towards the left. So basically, the builder's assistant will be pushing the ladder too hard towards the right. It will want to slide up the wall, the ladder, and therefore towards the right at point A, and the frictional force will go towards the left to oppose that. So those are the two possible positions of the frictional force. We'll go over that in more detail in part B. So going back to part A, we're trying to work out the reaction force on the ladder from the wall at point B, so we can do so by taking moments. We can take moments about point A. So let's first identify which forces have moments and whether they're clockwise or anti-clockwise. So there's 3 forces that have moments. There is W, 7W, and then R2 over here. So the forces that we have acting at A, R1, P, and the frictional forces, those all act through the pivot point at A. They therefore have no perpendicular distance to that pivot point. If there's no perpendicular distance, there won't be a moment. So none of these forces have a turning effect at point A. W and 7W, they will both have clockwise moments. So if you follow the directions of the arrows, they will take you clockwise around this pivot point here. And then the R2 force has an anti-clockwise moment about point A. Clockwise moments are equal to anti-clockwise moments. A moment is equal to force times distance, but we have to find either the perpendicular component of force or the perpendicular component of distance or displacement. In these scenarios, I personally prefer to find perpendicular distance, so I'm going to do it that way. Let's start with the 7W. So 7W acts in this direction, straight down. The perpendicular distance from the line of action of this force to the pivot will be this distance here. That's perpendicular to the line of action of the force, going towards the pivot. That distance there would be this whole triangle, or would be worked out by using that whole triangle. This would be the hypotenuse of 2A. This is a right angle. this will then be 2a cos alpha using SOHCAHTOA. So this distance is 2a cos alpha. Then there is this force here, W, that acts directly in the middle of this uniform rod. And it's just a triangle that's similar to the one that we have here, but just half its size. So the hypotenuse is now a rather than being 2a, and therefore this perpendicular distance here would be a cos alpha. And I don't think I have much space to write that, so I'll just say it. This distance here is a cos alpha. We're considering this triangle. Hypotenuse is a. This will therefore be a cos alpha. It's a right angle triangle. And then finally the force R2. R2, the perpendicular distance would be, so draw the line of action of the force, or in this case I'll point it out using this laser. This is the line of action of the force. The perpendicular distance will therefore be this. That's the perpendicular distance, which is actually the same as this length over here, which is 2a sine alpha. Using this triangle again and SOHCAHTOA. Okay, so then clockwise moments are equal to anti-clockwise moments. So let's start with the clockwise ones. We have W multiplied by a cos alpha. That was again this distance just here, so half of the entire length, a cos alpha. And then plus the 7W times 2a cos alpha. And that would be equal to the anti-clockwise moment, which would be R2 multiplied by this distance of 2a sine alpha. So that's equal to R2 times 2a sine alpha. The a's all cancel, and each of these three terms, this one, and this one, involve either cos or sine. And the coses and sines, they both have root 29 as their denominator. So when we replace the cos alpha and the sine alpha with these two numbers, they'll all be divided by root 29. Those root 29s will just cancel, so we can just ignore them from the beginning. This term here will be W times cos alpha, so W times this, so that'll just be 2W. Again, the root 29s just cancel. And then plus 7 times 2, so 14 times cos alpha, so times by this 2 over here. So 14 times 2 is 28, so plus 28W is equal to 2 sine alpha, so 2 times 5, that would be 10 R2. This is then 30W is equal to 10 R2. R2 is then equal to 3W, which is what we wanted to show. And then on to part B. So part B says to find in terms of W the range of possible values of P for which the ladder remains in equilibrium. Okay, so this goes back to what we were talking about at the beginning of part A. The frictional force can either act towards the left or right, depending on how hard the builder's assistant is pushing towards the right with this force P. So just to recap that, if the builder's assistant pushes very hard towards the right, the ladder wants to slide up the wall, and therefore at the bottom towards the right, the frictional force therefore acts towards the left to oppose that. The other scenario is if the builder's assistant does not push very hard towards the right, or at all even, and in that scenario it's just the frictional force towards the right that stops the ladder from sliding down the wall or towards the left at point A. So builder's assistant pushes hard towards the right, frictional force acts towards the left. If he doesn't push very much, the frictional force helps the ladder from stopping sliding down the wall and acts towards the right. The next thing that will be useful to do is to work out what the max frictional force would be. So we can do that by considering F max is equal to mu r. Mu is a quarter r. Okay, we want to work out the reaction force at point A. So upward forces equal downward forces. The system is in equilibrium, so therefore upward forces equal downward forces, forces to the right equal forces to the left. In the vertical direction, R1 going up is equal to W plus 7W, so is equal to 8W. So a quarter times 8W, the max frictional force is therefore 2W. Okay, so looking back at our diagram, we worked out that R2 is equal to 3W. Therefore the frictional force, if the builder's assistant were not doing anything at point A, we're not pushing the ladder towards the right, the frictional force of F going towards the right to counteract this force of 3W towards the left is not enough. We just worked out F to be 2W, that's not big enough to counteract this force of 3W. The minimum force required from the builder's assistant is therefore going to be 1W, so that these two forces add up to make 3W to counteract this. I'll write that out. So just considering the blue scenario. So the blue scenario is when the builder's assistant is pushing with the least possible force towards the right. So I'll call that P-min. P-min plus F, those are the two forces acting towards the right, F plus P. They will equal to the 3W towards the left. And in that scenario, P-min would be 3W minus the F. F is 2W, 3 minus 2 is obviously 1. This becomes W. That's the minimum pushing force. The maximum pushing force is when the frictional force acts towards the left over here. In that case, P towards the right, this force of P towards the right is equal to F and the 3W going towards the left. So P is equal to F plus 3W. So P max is F plus 3W, which will be 5W. That's our maximum pushing force. So therefore, the range of possible values for P would be W and 5W. It's between those two values. And then finally for part C. Often in practice, the builder's assistant will simply stand on the bottom of the ladder. Explain briefly how this helps to stop the ladder from slipping. Okay, so going back to our force diagram. If the builder's assistant is standing on point A, they're no longer pushing towards the right, so P no longer exists. If they're standing at point A, that increases the downward force on the ladder. We already have 7W going down here, W going down there. We'll have another weight force going down here. That increases the overall downward force on the ladder, and the upward force of R1 on the ladder must therefore increase to compensate for that. If the reaction force at A increases, that increases the frictional force, or the max frictional force. F max, the max frictional force, is equal to mu r. If the maximum frictional force is equal to mu r, and the reaction force here increases, we therefore have more frictional force available. Remember from the previous question from part B, the max frictional force was 2W, and that wasn't enough to counteract this 3W, but if the builder's assistant stands here and increases therefore this reaction force, that can increase the frictional force enough to be equal to this force that we have over here of 3W. But that wouldn't be enough to get the 3 marks. We also want to then talk about whether this force of 3W is affected by the builder's assistant standing on the ladder at point A. If they stand at the ladder on point A, the moments don't change about point A. They apply a force, the builder's assistant applies a force at the ladder at point A, a downward weight force. The moment of that weight force about point A is 0 because there is no perpendicular distance. The force acts through A, therefore there is no moment of the builder's weight or builder's assistant's weight at point A. Therefore, when taking moments about A, we still just consider the forces of W and 7W. That's how we worked out this 3W in the first place, by using these two forces or these two moments. They're not changing, and therefore the moment of 3W, or the force of 3W, will not be changed either. If the force of 3W is not changing, then the requirement on our frictional force doesn't change. It still needs to just be 3W. So to summarize, when the builder's assistant stands at A, that increases the downward force on the ladder, therefore increasing the reaction force, therefore increasing the frictional force. And because the moments about A are unchanged, when the builder's assistant stands at point A, the reaction force at B does not change, and that will be what we need to say for those 3 marks.